Hello, dear listeners. I'm excited and grateful to be presenting my research work, Impact of Drug Polymer Complexation on Dissolution and Recrystallization of Amorphous Solid Dispersions containing a weakly basic drug and HPMCAS in DRPI US. Amorphous solid dispersions are a potential formulation strategy to improve solubility and dissolution rate of poorly water-soluble drugs. Upon dissolution, ASTs form a supersaturated drug solution that leads to improved absorption and bioavailability in comparison to the crystalline drug. ASTs primarily consist of a hydrophobic drug molecularly dispersed in the matrix of a hydrophilic polymer. HPMCAS is the second most used polymer after PVPVA in formulation of ASTs. It is an acidic, ionizable, and pH-sensitive polymer with a pK of 4.97. Solubilization of HPMCAS occurs in 4 stages. The first stage is diffusion of water into the polymer matrix. The second stage is ionization of succinyl groups of HPMCAS with liberation of protons. Third stage is hydration that happens only when HPMCAS is sufficiently ionized. The fourth stage is diffusion and solubilization of polymer chains into the bulk solution. Because of polymer ionization and release of protons, gel layer pH is less than the bulk solution. Therefore, polymer ionization, polymer interactions with the aqueous environment, and drug-polymer interactions can considerably alter the dissolution outcome of HPMCAS ASTs. The objective of the current research was to investigate drug-polymer complexation of a weakly basic drug bedaquiline with anionic polymer HPMCAS. The second objective of the research was to develop a biorelevant dissolution method that can overcome drug polymer complexation in the solution. Bedaquiline is a weakly basic drug with a pK of 8.51. At pH 1.6, bedaquiline has a solubility of 67 microgram per ml. With increase in pH to 5.8, there is a decrease in bedaquiline solubility to less than 0.1 microgram per ml. Based on the solubility profile and log P of 7.13, bedaquiline has been classified as a BCS class 2 molecule with solubility and dissolution rate limited absorption. However, there is a twofold increase in bioavailability of bedaquiline when it is administered with food. As can also be seen here that in biorelevant media, fasted state version 1 media, which has a pH of 6.5, bedaquiline has a solubility of just 7.8 microgram per ml. However, in fed state version 2 media, which has a pH of 5.8, bedaquiline has a fairly high solubility of around 258 microgram per ml. Based on these physicochemical properties, bedaquiline is a good candidate for formulation into ASTs. We prepared ASTs of bedaquiline with HPMCAS using the solvent evaporation method. 5, 10, 20, and 30% drug loading ASTs were confirmed to be amorphous from modulated DSE and PXRD analysis. We then performed two-stage dissolution of 5% drug loading AST. At stage 1, the initial pH was 1.6, and at 60 minutes, we used a concentrated buffers to switch the pH of the dissolution medium to 6.5. At pH 1.6, bedaquiline release was only 10 microgram per ml. This is because HPMCAS does not ionize or solubilize at this pH. However, we expected that at pH 6.5, HPMCAS would solubilize and release bedaquiline. But counterintuitively, bedaquiline release was only 25 to 30 microgram per ml at pH 6.5. And at the end of the dissolution experiment, we observed an insoluble residue at the bottom of the dissolution vessel. Upon PXRD analysis, we confirmed that this residue was rather amorphous. This clearly ruled out matrix or solution recrystallization of bedaquiline as the probable cause for poor release behavior at pH 6.5. Therefore, we investigated drug polymer complexation as the second reason for poor release behavior of bedaquiline HPMCS ASDs at pH 6.5. Drug polymer complexation was studied using a co-precipitation method. For the study, we prepared two sets of samples. In the control samples, we dissolved HPMC AS stocks in buffer pH 5.8, 6.5, fed state version 2, and fasted state version 1 media. And in each case, we obtained a clear solution. Each solution was analyzed for polymer concentrations using UV visible colorimetric method or HPLC equipped with ELSD detector. In the test samples, we dissolved bedaquiline and HPMC AS stocks in the same media. However, in this case, we observed turbidity and precipitation. This was because both drug and polymer are ionized at pH 5.8 and 6.5, and due to electrostatic interactions, they form a hydrophobic ion pair complex. This insoluble residue was separated using ultracentrifugation and was analyzed in FTIR. The supernatants were analyzed for polymer concentrations. In FTIR spectra, we observed carbonyl peak at 1720, which confirmed presence of HPMC AS in the insoluble residue. Presence of bedaquiline in the insoluble complexation residue was confirmed from aromatic CN and aromatic CC peaks observed at 1250 and 1450 respectively. The next image here depicts percentage polymer complexation when stocks containing different molar ratios of bedaquiline to carboxylic acid groups of polymer were added into different media. At pH 5.8, we observed 90% polymer complexation. And when pH was 6.5, percentage polymer complexation was lower and 60%. This was because of greater extent of HPMC AS ionization and solubilization at pH 6.5 in comparison to pH 5.8. And in biorelevant media, fasted state version 1 and fed state version 2 media, percentage polymer complexation was only 20%. This was because of micellar solubilization of bedaquiline that freed succinyl groups of HPMC AS for hydration and solubilization. Based on these results, we estimated that dissolution profiles of bedaquiline HPMC AS ASDs would be significantly better in the biorelevant media. At pH 6.5, bedaquiline release was only 30 and 10 microgram per ml from 5 and 10% drug loading ASDs respectively. This was because of drug polymer complexation, which prevented hydration and solubilization of HPMC AS, which in turn prevented bedaquiline release from the polymer matrix. In fasted state media, where we have micelles, we observed complete release of bedaquiline from 10% drug loading ASD. However, with increase in drug loading to 20%, bedaquiline release dropped to 80 microgram per ml. In fed state version 2 media, we observed complete release of bedaquiline from 20 and 30% drug loading ASDs. This was because of greater abundance of micelles in the fed state media in comparison to the fasted state media. And we also observed previously that bedaquiline had a fairly high solubility of 258 microgram per ml in the fed state media. The conclusions drawn from the research work were drug polymer interactions impede dissolution of HPMCs ASDs because of differential polymer ionization, hydration, or formation of an insoluble hydrophobic ion pair complex. HPMC-AS has the tendency to form hydrophobic ion pair complex with cationic weakly basic molecules if they have contrasting pK values and are sufficiently ionized at a particular pH. With increase in pH, drug polymer complexation reduces because of greater extent of HPMC-AS ionization and solubilization. Micelles, on the other hand, disrupt ion pair complex by solubilizing the drug, and therefore we achieved complete release of bedaquiline from 20 and 30% drug loading ASDs in fed state media. However, it is important to establish relationship of in vitro biorelevant dissolution testing with in vivo performance of such complicated systems. Thank you so much for your patience, time, and listening.